Recording in progress.
Okay, thank you. Yes, thank you. So hello everyone. I'll present this paper called Gaussian Imagination in Bandit Learning, which published very recently, or like just in February. And so the outline of the talk would be that I'll give a very short introduction about Bandit learning, and then I'll go through the main paper, and at the end, some conclusion. So please feel free to ask any questions you have. I'm very new in this field, so I might not be able to answer all of your questions, but I just like to think together. That would be nice. Okay, so it's actually very related to what Bad presented like a month ago about online learning. So a Bandit problem is a sequential decision-making problem between a learner or an agent and an environment which we show by E. The environment is totally unknown to the learner, and all the learner knows is that the environment lies in some set, which we call the environment class. I'll explain the environment in more details in a couple of next slides. And the game is played over T rounds, which we call it time horizon. And at each round, at the beginning of each round, the agent first chooses an action from a given set. We are assuming that the set is fixed. It's not changing over time, but in a more general Bandit setting, the set can change, or it can be a compact set from RD. But here we are assuming that the set is fixed and it's a finite set. And when the agent chooses its action, plays it, then the environment at the beginning of the next round reveals some reward to the agent based on the action the agent has taken so far. Obviously, the agent doesn't have any information about the future. And so the actions only depend on the history, which we denoted by a sequence of pair of actions and rewards. And we show it by HT. And the set H here is just a union of all the possible histories that can happen in the environment. And we have something called a policy, which is basically the algorithm that the agent chooses for its actions. And it's a mapping from the history to the action set. So it gives a distribution over the actions for each realization of the history. And the agent just samples from this policy and plays according to that action. And a bit more about the environment. In a simple setting, the environment is just a distribution over a distribution for the reward function for each action. So environment gives a reward distribution for each action the user can take, and we are assuming that the distribution is fixed, it's not changing over time, and the agent's actions doesn't change the environment. So the environment is fixed at the beginning as well. And now we can define something called the mean reward, which is the expectation of the reward distribution conditioned to the environment we have. And so obviously this vector theta, which is the mean reward vector, has the number of the elements is equal to the number of the action set. And so for each action, we have a mean reward parameter, which is unknown. We don't know theta, we just know that it exists. So, So if the agent knew all the information about the environment, which means that if the agent knew all the thetas, then the optimal thing to do was to just choose the action that has the highest mean reward, which we call it by the optimal action. We show it by A star. And if there are multiple optimal actions, we can just randomly sample from them. And the reward we get by playing, the expected reward we get by playing the optimal action is called the optimal reward, which we show it by R star. But obviously, because the agent doesn't have the full information about the environment, doesn't know the theta vector, so it cannot play the optimal, it cannot get the optimal reward. So we define something called the regret, which is the difference of the total expected reward we get by playing the policy we've chosen, compared to the optimal reward. And the goal of the agent is to choose a policy that minimizes the regret. And so we call a good policy, a policy is a good policy when it converges to selecting the optimal actions as time goes to infinity, right? So, or in other words, we can define that a policy is a good policy if the limit of regret over time for that policy goes to 0. This is what we call the optimal policy. Information about the environment. But in the Bayesian setting, when we have a Bayesian agent, the agent assuming that there is a prior over the environment parameters. For example, if the environment is putting a Bernoulli distributions for the reward functions, the agent is assuming that the parameters of that Bernoulli is coming from a beta distribution, which is the conjugate prior for the Bernoulli. And then the agent chooses its policy, act based on that policy, and after receiving the rewards for that action, it can update its posterior based on the observed action reward pair. This is what we call the Bayesian agent. It's just the notations. And as I said, a good policy is a policy that that tries to find the optimal action, which means to estimate the theta parameter better and better. So a good policy should keep a good balance between something called exploration and exploitation. Exploration is when the agent has to explore through the whole action set. Because if we just stick to a subset of the action set, we might just lose there's a positive chance that we just lose the optimal action. So we never converge to the optimal action. So we have to explore through the whole set in order to find better rewards, better actions. And exploitation is when we are taking advantage of the whole history we have, which means that if so far we've seen, for example, an action is bringing very low rewards, we have to stop using that because it's not really optimal action. So we have to take advantage of the history we know so far. And the whole thing just summarizes in finding the good policy, which keeps a good balance between exploration and exploitation. So these are two very famous bandit problems. One is Bernoulli bandit, as I mentioned before, that the rewards are coming from a Bernoulli distribution with the mean reward theta A. And in the Bayesian setting, we are assuming that for each theta A, there is a prior of beta distribution. And we are assuming that it's a beta distribution because it's conjugate prior for Bernoulli, and it just is all the computations. And for the Gaussian bandit, we are assuming that the rewards are sampling from a normal distributions. And again, in the Bayesian setting, the prior is also normal. So these are the two very famous examples of bandit learning, which we will use these two examples in the main paper as well.
The prior is on the Gaussian prior is on the mean, on the log variance or something like that. I'm confused by the.
Sorry, where?
So you put a prior distribution on the mean on the variance, no?
Only on the mean. Yeah, we are assuming that the variance is fixed.
Oh, okay.
Yeah, only on the mean. Yeah, sorry. Yes. Before going to the main paper, we just need one more definition, which we called it information ratio. So information ratio is defined as the square of the regret the information ratio is defined at each time step, and it's the square of the regret at that time step over the information gain we get by playing the pair of the action we've selected and the reward the environment gives us. So it's basically shows that how much information we'll learn about the environment by playing this pair of action and reward. And the interesting thing about the information ratio is that it actually shows a very interesting trade-off between exploration and exploitation, because if we want to, so let's see when psi is very small. Psi is very small when the regret in the numerator is very small. In that case, it means that we are exploiting the history very well because we are playing very close to the optimal case, which is the exact term as exploitation. Or it's very small when the mutual information is very high, which means that by playing this action, we are gaining a lot of information about the environment. So we are exploring a lot about the environment. So a good policy could be a policy that minimizes the information ratio at each step. This is actually called information directed sampling algorithm, which gives us a policy, an optimal policy. But we can generalize the definition of the information ratio by changing three things. So the first thing is that we can just get a supremum. So the information ratio here is defined for each time step. In the general case, we can define it by getting a supremum over all times and over all the possible histories. So the first thing that changes is this supremum here. The other thing is that we are letting ourselves to not comparing ourselves with the optimal case, but to a tolerated version of it. So we are giving ourselves a tolerance epsilon here, which means that we are just comparing ourselves to the R star minus epsilon instead of comparing ourselves to the optimal case. And of course, epsilon can be very, very small, so it's not a very limitation. And instead of defining information ratio with respect to the environment, we are defining it to something called the learning target. We denote it by chi. And chi is a random variable, which is independent of the whole history conditioned to the environment. The reason we are, so obviously environment itself can be a learning target, right? So the chi is just a general case. Environment is still can be, chi can be equal to the environment. But the hope of, we are defining chi in the hope of that, so basically, the full information we can gain about the environment is roughly the entropy of the environment, which can be very big and intractable. So we are hoping by defining the learning target, the mutual information between the learning target and the environment would be much less than the entropy of the environment. Would be much less than the entropy of the environment, but it's still rich enough to help us to distinguish the actions from the optimal action. So we can still find the optimal action, but we are learning faster and faster. And this generalized version of the information ratio is called gamma, which we'll use in the main paper. So far.
You're going to give us an example of the way you build chi, because it's not super.
Oh, yeah. Yeah, so yeah, actually the gamma is the gamma and psi, I don't give any example, say some things about it. Gamma and psi are very abstract concepts because, so here we are assuming that we are comparing ourselves to the optimal case, but we don't know the optimal case. So we have to somehow estimate gamma when we are trying to find a policy based on gamma. And so in the Bayesian setting, when we have some priors, we can somehow estimate the regret term in the numerator. But yeah, it's a very abstract just definition, like a very abstract definition.
have like an intuition, like what an example of chi could be?
Yeah, so chi could be any any statistics about the environment. For example, it could be actually the mean reward of the environment instead of just comparing the whole environment. Or if we have like some, for example, if you have some mean value and variance, we can just focus on the mean value and just ignore the variance, for example. Or any other characteristics about the environment can be the learning target.
So any function of E, basically.
Yeah. At least that's my intuition about it.
So I guess given all the because E here is some higher. That's why it's given E. It's not a constant in that condition.
The environment?
Yeah, exactly. It's a random variable with some from the prior.
Yeah.
Okay.
Yeah. Okay. So the first theorem, which gives an information theoretic regret bound, is basically says that the regret can be bound by this term. I didn't provide the proof here because it's very straightforward. You just need to basically write the definition of the regret and then use the definition of the information ratio because sorry, the regret was this term. And if we just, so we have the expectation of R star minus the reward we get at time step t plus 1, which is basically the multiplication of these two terms. It's the denominator in the gamma term, and then we can basically reach this upper bound by using just some very simple lemmas like Cauchy-Schwarz and something like that. But we assume that the agent knew the true environment.
Coming back, can you get, I mean, do we know it's tight or what can we say about this bound? Okay, we have this bound, but it's super loose or in some cases quite tight.
Yeah, it depends on the algorithm, the policy you choose, because obviously gamma is dependent on the policy.
Sure.
Yeah, for example, for information directed sampling and Thompson sampling, it's just order of square root of t, which is very it's a very tight bound. It's the optimal bound. Okay, so far we assume that the agent knows the true environment. For example, it knows that the environment is a Bernoulli or a Gaussian environment. But the question this paper has tried to answer is that what if the agent has misspecified beliefs? What does this misspecification mean? It means that there is a true environment E, which we call it the real environment. But the agent believes that it's playing in another environment called the imaginary environment. So for example, the real environment is Bernoulli. The rewards are coming from a Bernoulli distribution, but the agent believes that it's playing in a Gaussian setting. So the agent is acting based on the imaginary belief it has, based on its own belief, but the rewards are coming from the true environment. And obviously, the policy that the agent can choose might not be the optimal policy for the true environment. So the bound can be very bad. The regret bound can be very bad. And that's basically the main question this paper has tried to answer, which says that can we upper bound the regret when the agent has misspecified beliefs? And so answering to this question can be very difficult because it can depend on a lot of parameters. In this paper, they focused on just one specific setting where the true environment is Bernoulli and the imaginary environment is Gaussian. And so they answer yes to this question. We can actually boundary grid with good terms. But for the general case, it's an open problem, I guess. So we need to reformulate the concept we had before just to adapt it to the misspecification concept. So for the real environment, everything is same as before. We have a mean reward vector theta. The rewards are coming from a Bernoulli distribution, and the prior distribution is a beta function. And the optimal action and optimal mean reward are shown by A star and R star. And for the imaginary environment, E tilde, the user assumes that there is a mean vector theta tilde, which takes real values, and it's coming from a normal distribution. And we're assuming that sigma here is fixed. And the mean reward is coming from a normal prior. And again, the user believes that there exists an optimal imaginary action and an optimal imaginary reward called A star tilde and R star tilde. And so what happens in the real world is the real history. So H of t defined same as before is the real history. And again, H here is just the union of all possible all possible histories. And but the agent again believes that there could be other histories as well, because it believes that it's living in another environment. So it is useful to define the imaginary history, which denoted by H tilde, and it's a sequence of possible pair of action and pair of imaginary action and imaginary rewards. So at each time step, the agent observes a realization of true history. So a realization of HT here, but it believes that the observation is a realization of H tilde. And in this specific case, HT is a subset of H tilde because the rewards here are binary, 0 or 1.
Not super realistic, because after having seen two observations, you're like, oh, it's 0, 1. How can it be a real value? Reject. No, it's okay. Sorry.
Yeah, so here HT is a subset of H tilde. And so we can modify the information ratio as well. It looks like the same as before. Everything is in the imaginary environment. The only difference is that in the definition of the information ratio, when we were getting the supremum, we were getting the supremum over all the possible histories. But here, the only histories that can actually happen are the histories from the real environment. So the supremum is over the real histories. And because, as we mentioned, HT is a subset of H tilde T, this gamma here is upper bounded by the case when the supremum was getting over H tilde. So it's by gamma tilde. And it's basically gamma tilde is the information ratio if the agent was actually playing in the Gaussian environment. And yes, that's it. We only need one more definition, and then we're good to go to the domain theorem. So the definition is called change of measure. If we have two random variables, x and y, and corresponding images, for any realization of y, we can define the conditional distribution of x given y, which we show it by f of y as a function. And this function is well defined for any other random variable z. So f of z is well defined if the image of z is a subset of image of y. And to show what f of z means, we show it by this term here. It's the distribution of x when we change the measure from y to z. I don't know how I can like explain it better. Yeah. Yeah, sorry. Is it okay? Yeah, okay. I'm happy.
You can define that, why not? I agree.
And so we call it a change of measure. And since we have defined the distribution, the probability, now we can define expectation, entropy, and mutual information, all based on that change of measure. So all of these concepts are well defined. And so now we can move on to the main theorem with two assumptions. The first assumption, which is called optimism, basically says that for any time step t, this inequality holds. And this assumption one actually requires that the imaginary environment should be in a way such that the agent's expected imaginary reward would be greater than the real optimal reward. Why are we assuming this? Because so if the agent's imagination of the optimal reward is less than the optimal reward itself, then the agent would just stop exploration after a while, because it has already found the it can really easily converge to the imagination of itself. So it won't explore anymore, and the bound would be very, very loose. So we have this assumption just to ensure that the bound has some meaning. The bound wouldn't be very meaningless. And the intuition behind it is that if the prior we are assuming for the environment has a very large variance or is diffuse enough, this assumption easily holds. So it's not a very difficult assumption to meet.
Expectations over?
Over all the randomness? Yeah, the first one is over all the randomness other than the history, and the other one is over the randomness in the history. And the second assumption, which is called Gaussianity, just basically says that the imaginary learning target chi tilde and the imaginary mean reward theta tilde are jointly Gaussian. Again, it's not very restricted when we are assuming that the environment is Gaussian. It only ensures that the environment admit the prior Gaussian, the posterior Gaussian for the problem.
I'm sorry, I don't get this learning target yet, so I don't understand this assumption.
Yeah, so it's not really important. You can just assume that chi tilde is the environment itself.
Okay.
Yeah, it's just it's an option for chi tilde. Yeah. And the main theorem basically says that if these two assumptions hold, then for an agent that's interacting with a Bernoulli bandit environment, E, while believing that it's playing in the imaginary environment, a Gaussian imaginary environment, E tilde can be bound, the regret can be bound by this term here. So if we just look at the first two terms, it's actually the regret the agent could get if it was really playing in a Gaussian imaginary environment. And the last term just shows, just comes here because of the false belief we have. because we are believing we are playing by theta tilde, but we are actually playing by theta. So this is just the discrepancy between the true environment and the imaginary environment. Yeah. So I'll go through the proof of the theorem. I hope just it clarifies a bit more. To prove the theorem, we need to break it down into two steps. At first step, we show that under assumption one, we upper bound the regret by a sum of two terms. One thing we call imaginary regret, and the other is the KL divergence term we had here between theta and theta tilde. And we just upper bounding using assumption two. Okay, so for the first step, we want to show that under assumption one, the regret can be upper bounded by these two terms. The second term is basically what we had in the main theorem. So how to show this is to start by composing the one-step real regret. So one-step real regret is this term here. The expectation between the regret, the reward we get at this time step by playing action AT, comparing to the optimal reward R star, and we can just we can just rewrite it as two expectations. One given and then the expectation over HT. So this is basically what we've done in the second term. We also added and subtracted this term. And if we just rearrange the terms, we get to this like ordering. And the term here we have is under assumption one is always less than or equal to 0, because we thought that the imaginary optimal reward is always greater than the optimal reward. So this term is always negative or 0. So we can upper bound the one-step real regret by this term here and this term here. So the first term is what we call the, and if you just look at the first term we had in the upper bound, it's basically the same thing. We just need to get the summation over time. And the second term is what we called one-step approximation loss. And as you see, it's just comparing the real regret we receive from the environment, their true environment, comparing to the reward we were expecting to receive. And we want to be able to upper bound this second term by the KL divergence between case, if R tilde was a discrete random variable similar to R, which is a binary random variable. If R tilde was a discrete random variable, we could have easily proved the main bound, because so using this lemma, were said that if X and Y were two discrete random variables that were bounded, then we can upper bound the difference between their expectation by the total variation between their distributions. So we could have upper bounded, if R tilde was a discrete random variable and was bounded, we could have upper bounded this by the total variation between the rewards. And then using Pinsker's inequality, we could have upper bounded by the KL divergence. And then by using the chain rule for KL divergence, after getting the summation over time, we could have reached the main bound. But so the technical issue here is that the imaginary rewards aren't discrete. They are coming from a Gaussian distribution, and they are not bounded. And the KL divergence between the rewards, one coming from a discrete random variable, one coming from a real valued random variable, is just infinite. So we can basically use the previous lemmas. And I guess this is the interesting part of the paper. They proposed something called auxiliary reward. The auxiliary reward basically mimics all the behavior of the imaginary reward, but it is discrete. So they use this auxiliary reward to, instead of comparing the true reward with the imaginary reward, comparing it to the auxiliary reward and then imaginary reward. And the auxiliary reward is bounded. I don't know if it's a trivial technique or not, but it was very interesting for me. So the lemma that says that this auxiliary reward actually exists is this lemma, which is a bit long. I didn't provide the proof because it was a very long proof, but yeah. But the lemma basically says that we can construct the auxiliary reward vector. I don't know how I should read this symbol, but okay, just the auxiliary reward vector. We can construct the auxiliary reward vector, which takes discrete values and has these 4 properties. So the first property says that the R tilde, the auxiliary reward for each action at each time step has a strictly positive probability mass on 0 and 1, and is bounded by 2 gamma, which gamma is the term here we had. And we can define the auxiliary history, which is again a sequence of pairs of auxiliary actions and auxiliary rewards, while the auxiliary actions are basically coming from the same policy we've chosen for the imaginary environment. So the auxiliary actions are the same thing we had for the imaginary environment. That's why the auxiliary reward actually mimic the same thing, the same behavior from the imaginary reward, because we are taking the same actions. And the third property says that if the theta tilde for action A is a number between a number between 0 and 1, then condition to theta tilde, the auxiliary reward is distributed according to a Bernoulli distribution. So it's a discrete random variable. And almost surely the expected imaginary reward is upper bounded by the expected auxiliary reward for each time step and for each action. So they basically prove that this auxiliary reward exists and we can construct it. And now we can use this auxiliary reward. So if we go back to the imaginary reward we had here, sorry, the imaginary, the one-step approximation loss we had here. This is basically this term. And by the property 4 we had in the lemma, in the auxiliary reward lemma, we know that the imaginary reward can be upper bounded by the auxiliary reward. So this inequality holds. And now, since R tilde is a discrete random variable, and now R is also a discrete random variable, and both are bounded, now we can use the previous lemmas. So by the total variation lemma, we show that this inequality holds from line 2 to line 3. And then by using the Pinsker's inequality, we can prove that the approximation loss is less than the KL divergence between the rewards of the true environment and the rewards of the auxiliary environment. And then if we get the summation over time, this is basically the previous term. We just added the summation over time here. Then it would, using the Cauchy-Schwarz inequality would be less than the third line. And now using the chain rule for KL divergence, this term here can be upper bounded by decayal divergence between the real history and the auxiliary history. And now, as we said, the auxiliary history and the real history are following the same actions. So the actions in the histories doesn't have any more information than the rewards. So using the data processing inequality, we can just upper bound it by the rewards of the real environment and the auxiliary rewards. And now again, by using the data processing inequality and knowing that both of these rewards are coming from Bernoulli distributions, one with parameter theta and one with parameter theta tilde, we can upper bound it by the decayal divergence between theta and theta tilde, which basically gives us this bound here. And then we are done. So the first step is complete. And for the next step, for the second step, we want to show that under assumption 2, which was the Gaussianity, we can upper bound the imaginary regret by the term we have here, which is the regret we have if we were playing in the imaginary environment. I again didn't provide the proof of this step because it's again very, very simple. We just need to use the definition of the information ratio here, and then just open the mutual information by entropy terms, and a lot of terms just cancel each other and we get the upper bound. It's a very straightforward proof.
Is the definition, the way they define the auxiliary reward,
the imaginary? Sorry, what? The imaginary?
The auxiliary, when you define this discrete reward, auxiliary reward before.
Yes.
Is it strong? The proof is strongly dependent on the fact that you're Gaussian or not? To obtain the result.
To obtain the bound?
No. Can you go to the definition?
To the definition of the.
Yeah. So is it strongly dependent on the Gaussianity in the imaginary environment or not?
For the proof of the lemma, it uses, but it's not strongly dependent. I guess the technique can be extended to other.
Why you are doing that? They have to go for that to get a bond.
Yeah.
To the bond. Doesn't seem really direct. I'm sure.
Yeah, I didn't know if it was a trivial trick for this type of problems, but it was very interesting for me.
But it seems a bit not natural for sure. Interesting.
Yeah, I guess that was the main contribution here. This trick was the main one. And yes, and then by just combining the result of the first step and the second step, we get to the main bound. So as the conclusion, this paper just showed that any learning algorithm or any policy that works good for the Gaussian environment, like Thompson sampling, information directed sampling, if we assume that the prior is diffuse enough, we can still use that algorithm, that policy for the case we have a Bernoulli environment, but we are acting according to the Gaussian bandit. So it's very robust to the misspecification. Actually, the bound for the Thompson sampling, the real bound, if we know that we are playing in the Bernoulli distribution, is of order square root of t. But here the bound can be proved to be like t log of t, which is not really that bad. So it's actually a very good upper bound for the Thompson sampling. Basically just pretending that the random variables are Gaussian could simplify a lot of calculations, a lot of implementations. And so dealing with the Gaussian distribution, it is much easier than dealing with a beta distribution. So this paper just showed that this Gaussian imagination can be justified when you have a Bernoulli bandit, which is interesting, I guess. But there are still lots of works because this is like the newest paper in this topic. And they are just solving the problem for a very specific case of Bernoulli and Gaussian. And it's still an open question for the general case or other type of bandits. And another question is for me is that while we are using the information ratio, which I guess everyone can agree, it's not very intuitive. It's just an abstract concept, but maybe we can define a better type of information ratios that can still.
It's because it's Van Roy, you introduced this information directed something, so he's trying to sell it again.
Yeah. Yeah. So. Basically that's it. Thank you. These are the references, and yeah, thanks a lot.
Thanks.
If you have any questions.
Why did, you write this paper, and why did you think it was it's interesting. I'm not saying it's not interesting, but why did you pick this one?
So I was interested in bandit learning, and I don't know, I just, after a couple of presentations, I realized that people might be interested in information theoretic bounds. So I wanted to pick something that's in the intersection of, and the question is actually interesting because I guess in a lot of cases, we don't have the full information about the environment, and we always have some misspecified beliefs. So it's interesting to know if we can use the previous process.
Another question. So you say, okay, we can use this bound for Thompson sampling. We go from root T to root T log T. Is it easy to? I guess they do it in the paper. But is it easy to go from their bound to establish this kind of weather for Thompson sampling, or is it quite?
The gap between the.
How do you get say T log T from the bounds?
Yes.
Presented, is it quite simple actually, the derivation?
Yes, if you just write the proof for the Thompson sampling and the information ratio for Thompson sampling, you get the. It's essential.
Can you hear me?
Yeah. Hi.
Yeah, great. Hi, Amitis. For the so interesting.
Thank you.
I had a question. You're saying that this analyzing like design for studying Gaussian analysis, typically to Bernoulli environments, right?
Yes.
And I was wondering if the environment was has a bounded support, but with maybe like heavy, instead of Gaussian, like Cauchy or something like that. Do you know what would happen? In the literature, what kind of bounds you could achieve the bandit like that?
Yes, actually, I don't know the answer to the question, but in the lemma they had to construct the auxiliary reward. The last property basically says that even though the imaginary regret is an unbounded imaginary reward is an unbounded variable, but the expectation is upper bounded by the auxiliary reward, which is a bounded variable. And I guess if we have like heavy tails, this property might not hold anymore. I'm not sure, but that's just the first thing that came to my mind when you were asking your question. But no, so I haven't found any other works that is focusing on other type of bandits. So yeah, I don't know.
Okay, thank you for your answer. And just one question. The expectation, take it with respect to fire, right?
Where here?
The expectation.
In this property?
Yeah, I mean it's everywhere in the
Yes, the expectation is over all the randomness in the policy, given the history that happened in the real world. Yeah.
Only, okay. Okay.
So for any history in the tree environment, this inequality holds.
Okay. Great.
Thank you.
So I'm done.
Thank you.
Having lunch downstairs in 15 minutes, 10 minutes. C'est pas comme ça,